Hello everyone, my name is Masoud Babai. I am an associate professor at Delft University of Technology. Today I will be talking about the role of current mode passive mixers and M-pass filters in modern RF receivers. I'll start with a quick introduction about the main performance matrix of the receivers and why it is essential to use current mode operation in the wideband receivers to deal with large in-band and out-of-band blockers. Then I will discuss the interesting characteristics of M-pass filters. I develop a compact model for them and investigate their drawbacks. As the next step, we use M-pass filter concept to synthesize a high-order bandpass filter and realize a magnetic-free circulator. Then I develop a design guide for the conventional mixer-first receivers, discuss the shortcomings of this structure and how state-of-the-art receivers dealt with that. Then we discuss some techniques using M-pass filters to improve the out-of-band linearity of the low-noise transconductance amplifier or LNTA-based receivers. I also have some slides about the harmonic rejection in wideband receivers, and we have the conclusions at the end. As can be gathered from this slide, the so-called sub-6 GHz 5G receivers must be able to cover an operating frequency range from 600 MHz all the way up to 7.2 GHz. Moreover, they must detect signals with different channel bandwidths from 5 MHz to 100 MHz. Consequently, multi-band, multi-mode receivers are highly needed when considering the growing number of frequency bands, modes, and channel bandwidths in the sub-6 GHz 5G new radio standard. After knowing the receiver operating frequency and bandwidth, we also need to estimate the required high-level receiver specifications in terms of noise figure and in-band and out-of-band linearity from the standard. The required noise figure is estimated by knowing the reference sensitivity level. The reference sensitivity is the minimum power level at which a desired signal with a certain modulation type and bandwidth can be detected with a specific throughput or bit error rate. For example, based on the standard for local area base station applications at the reference sensitivity level of -88 dBm, the throughput should be larger than 95% when receiving a signal with QPSK modulation and a bandwidth of 50 MHz. Please consider this figure for noise figure calculation. At the input of the receiver, the equivalent thermal noise level in 1 Hz bandwidth is -174 dBm plus the receiver's noise figure. Then the power of the noise at the receiver input is calculated by integrating the noise spectral power density over the desired bandwidth of 50 MHz. On the other hand, to reach certain amount of throughput, the power of the desired signal should be above the noise power by certain signal-to-noise ratio. As a result, we have the following equation. The impedance sensitivity is equal to -174 plus noise figure plus 10 log of the bandwidth plus the minimum SNR. For QPSK signals, we can estimate the bit error rate by the Q function of the root square of SNR. To reach less than 5% bit error rate, the minimum SNR is about 5 dB. By replacing all those numbers in the reference sensitivity equation, the receiver noise figure should be below 4 dB. Different in-band and out-of-band linearity requirements of the receiver can be calculated by considering different blocking scenarios in the standard. For example, for 5G local area base station applications, we have the following tests. The first one is the in-band blocking test, where the desired signal is 6 dB above the reference sensitivity and a modulated in-band blocker with -35 dBm of power and 20 MHz bandwidth is also present. We can use these two well-known equations to calculate the required in-band IIP2 and IIP3 of the receiver. PIM is the power of the intermodulated tone, which is about 12 dB below the desired signal level, not to limit the system bit error rate. The additional 6 dB and 9 dB terms are also included since the blocker is modulated. The second test is the closed-in blocker, in which a -15 dBm continuous wave blocker is located at 60 MHz offset from the passband edges. The required out-of-band IIP2 and IIP3 requirements are then calculated using these equations, where the extra 3 dB and 6 dB terms are included since one blocker is modulated and the other one is a singleton. Note that the filter order can be calculated by knowing the in-band and out-of-band IIPT values. The last test is the far-out blocker test, where the receiver should maintain its linearity and performance while dealing with a 0 dBm far-out blocker. As a result, the receiver blocker 1 dB compression point or B1 dB must be above 0 dBm. After concluding the receiver's high-level specifications, we need to choose a receiver architecture that offers the highest flexibility and reconfigurability in terms of operating frequency, channel bandwidth, and modulation. Moreover, it should be resilient to in-band and out-of-band interferences. The most straightforward way to achieve a reconfigurable transceiver is to employ a high-speed digital to analog converter as the transmitter and a high-speed analog to digital converter as the receiver. Based on the Nyquist criteria, the sampling rate of the ADC should be above the twice of the maximum operating frequency, which is here about 15 gigasample per second. The ADC signal to noise and distortion ratio should be more than 80 dB, considering the 0 dBm for the maximum blocker power and a quantization noise level below the thermal noise. Let's investigate if these specifications can be achieved by prior art ADCs. This plot summarizes the performance of state-of-the-art ADCs. The x-axis is the ADC SNDR at the Nyquist frequency, and the y-axis is the maximum input frequency of the ADC. The star shows the desired performance of the required ADC in this plot. If we consider the state-of-the-art ADC with 80 dB of SNDR, its speed is 360 times lower than the desired speed of the required ADC. On the other hand, if we consider the state-of-the-art ADC with a maximum operating frequency of 7 GHz, its dynamic range is 30 dB lower than the desired dynamic range of the required ADC. Consequently, current ADCs cannot satisfy the required ADC specifications by a large margin. Even considering a Schrader FOM of 166 dB, the required ADC would consume about 10 to 100 watt. Consequently, it is not feasible to efficiently implement the required ADC in the DAC/ADC-based software-defined radio structure. In the modern receivers, we have to use a frequency down converter to reduce the required ADC speed and employ different filters to decrease the required ADC dynamic range. This slide shows the block diagram of the conventional voltage mode receiver utilizing different filters and frequency down conversion to reduce the ADC's power consumption, dynamic range, and sampling frequency. In this structure, an external band select filter and a narrow band low noise amplifier or LNA are employed to prevent large out-of-band blockers corrupting the desired signal. Since RF filters have fixed frequency bands, several front ends are required to cover the large number of frequency bands serviced by a modern wireless device. Of course, by removing the external band select filter and adopting a wideband LNA, a single voltage mode receiver can cover the entire spectrum of interest. However, this structure cannot handle large interferences. Note that this receiver has no selectivity and amplifies both the desired signal and blockers. Given the voltage amplification needed to achieve a competitive noise figure, and also considering the low supply voltage used in nanometer CMOS technologies, a 0 dBm blocker will cause the LNA to saturate, thus increasing the receiver's noise figure and distortion significantly. Hence, the inability of this structure to handle large blockers has prevented its commercial use. In the wideband current mode receivers, the LNA is replaced with a linear transconductance, which derives current mode passive mixers. This structure has four main features. First, the input impedance of the baseband transimpedance amplifier is small at in-band frequencies and almost zero at out-of-band frequencies. Consequently, the voltage swing of the blockers is small at the input port of the baseband amplifiers, improving the receiver's linearity. Second, due to the transparency of the passive mixers, the baseband impedance is upconverted to RF, thus realizing a bandpass load for the transconductance. Hence, out-of-band blockers cannot saturate the LNTA's output. Third, to derive the mixers in current mode, the transconductance output impedance must be much larger than its load impedance. Fourth, before filtering, this structure avoids any voltage gain for out-of-band blockers, thus maintaining the receiver's noise figure and linearity. In the rest of the presentation, I will explain those features in more detail. First, I explain the impedance transformation property of the passive mixers in the context of N-pass filters. An N-pass filter is composed of a resistor, N baseband capacitors, and M different switches driven by M non-overlapping clock phases with a frequency of FLO. Consequently, the pulse width of each clock phase is TLO over M, in which TLO is the clock period. In this configuration, at any moment only one of the switches is on and connects its corresponding capacitor to the output node. If we look at the Vout over Vs transfer function, it is a bandpass filter with a center frequency of FLO and a bandwidth that is related to the number of clock phases, resistor, and capacitor values. Consequently, we can have a programmable bandpass filter with a high quality factor. In the next slides, I will intuitively explain how this works as a bandpass filter. First, I explain the operation of the N-pass filter in the time domain. In this example, M is equal to 8 and the input frequency is the same as the clock frequency. It means that the input signal exactly fits the sum of 8 clock intervals. During the first phase, V1, the first switch is on and the first capacitor senses the first part of the sine wave in blue. During the second phase, V2, the second switch is on and the second capacitor samples the second part of the sine wave in red. Similarly, in phase 3, the third part of the sine wave in green charges the third capacitor, and the same thing happens for the other branches until the last phase, V8. Now let's focus on the transient response of the first capacitor voltage V1. First, there is no charge in the capacitor and V1 is 0. Then the first switch is on and the blue part of the sine wave starts charging the capacitor. Since the time constant of the resistor and capacitor RC is much larger than the clock pulse width TLO over 8, the capacitor is charged a bit and its voltage goes up slightly. Then the switch becomes open and the charge stays in the capacitor and the voltage stays also the same. In the next clock period, the same part of the sine wave in blue again starts charging the capacitor and the capacitor voltage increases slightly. This procedure repeats in all clock cycles. After many clock cycles, we reach the steady state in which the capacitor voltage is equal to the average value of the blue part of the sine wave. The same thing happens for all other capacitors. The capacitor's voltages are related to the average value of their corresponding part of the sine wave. On the other hand, the output node senses the capacitor's DC voltages sequentially. Consequently, the output is a staircase approximation of the sine wave. You can also imagine if one increases the number of the clock phases, he will have more capacitors and a better approximation of the sine wave at the output node. Now consider the case in which the frequency of the input signal is not equal to the clock frequency. It can be larger or smaller. In this case, a capacitor looks at different parts of the sine wave in different clock cycles. Since the settling time is very slow, the average value of different parts of the sine wave is stored in the capacitor. Consequently, in the steady state, after many clock cycles, we get the same DC voltage for all the capacitors, meaning that the output signal is 0. As a result, for the frequencies equal to the clock frequency, Vout is the staircase approximation of the input signal, and for other frequencies, Vout is almost 0. And indeed, this is the definition of the behavior of an ideal bandpass filter. To develop a compact model for N-pass filters, I also need to analyze the circuit in the frequency domain and more mathematically. I apologize for that. To do so, we write the Fourier series of the LO clocks, where n is the number of the harmonics and the first term in blue is the magnitude of the Fourier coefficients, and the second term in red is the result of the phase shifts among different LO phases. Now consider the following system composed of m identical branches connected through a common node. Each branch consists of a baseband impedance ZBB in series with an ideal switch. We also have a current source with an infinite output impedance, and its current flows into the switching system. The switches are driven by m non-overlapping clock phases. In this analysis, we want to calculate the RF voltage across the current source in order to have a closed form equation for its load impedance. First, consider the first branch. The input RF current is mixed with the negative sideband of the first phase of the LO and generates a baseband current IBB1. This current flows into the baseband impedance ZBB, which is a low-pass filter here, and generates a baseband voltage VBB1, which can be calculated by this equation. Since there is no isolation between the mixer ports, the baseband voltage is mixed back with the positive sideband of the first LO phase and generates a bandpass shaped voltage at the RF node, which can be calculated with this equation. It is related to 1 over pi squared times sine squared of pi over m, an upconverted version of the baseband impedance. In a similar fashion, we can also do the same exercise for the other branches. The RF input current mixes with the negative sideband of the ith LO clock and generates a baseband current IBBI. The current flows into the baseband impedance and generates a baseband voltage of VBBI. Due to the transparency of the passive mixer, the baseband voltage mixes with the positive sideband of ith LO signal, realizing a bandpass shaped voltage at the RF node. The contribution of other mixing branches to VRF is the same as the first branch. Finally, VRF is the sum of all contributions from different branches, and accordingly, the load impedance of the current source can be calculated using this simple equation. It is indeed related to the baseband impedance ZBB, but shifted to the LO frequency along with a scaling factor of 1 over m times sinc squared of 1 over m. For m larger than 8, this scaling factor can be simplified to 1 over m. If the baseband impedance is a simple low-pass filter, this circuit transforms it to a high-Q bandpass filter at the LO frequency. Now let's develop a compact model for M-pass filters. I also added the on resistance of the switches in this schematic. Since only one of the switches is on at any moment, we can remove all the R-on resistors in the baseband ports of the mixers and put one R-on resistor at the RF ports of the mixers. As the next step, we can also replace all the switches and baseband impedances with an RF impedance ZRF that we calculated in the previous slide. Now we have this simple model for our N-pass filter. If we replace the baseband impedance with a capacitor, this model predicts that the system gain Vin over Vs is 1 at LO frequency. However, from our previous discussions, we know that Vin is a staircase approximation of Vs, and it can be shown that the gain of the system can be calculated by sinc squared of 1 over m, which is a bit smaller than 1. To consider the system loss, a shunt resistor RSH is also added in the model, and its value can be calculated by this equation in green. As can be gathered from the equations for RSH and gain, both the shunt resistance and gain are strong functions of the number of LO phases. By increasing m, Vin is a better approximation of the input signal, and the shunt resistance becomes larger, and the system loss becomes smaller. Even by m equal to 8, the system loss is as low as minus 0.45 dB. In a special case, we can replace the baseband impedance with the baseband capacitor. Then we have the following model and transfer function. The filter bandwidth can be calculated by this equation as a function of m, CBB, and Rs plus Ron. Intuitively, the factor of m is present since each baseband capacitor sees Rs plus Ron only 1/m of the time, and it feels like that this resistor is m times larger. The filter quality factor is defined as the ratio of the center frequency to the bandwidth. The center frequency is dictated by the clock and is in the order of 1 to 7 GHz, and the system bandwidth is in the order of tens of megahertz. Consequently, we can have a high quality factor of several hundred without any physical limitations. We can also create a continuous time equivalent model using parallel tank consisting of a shunt resistor, an equivalent capacitor, and inductor that resonate at the frequency of omega LO. Up to this point, we only discussed the good characteristics of the M-pass filters. However, there are some issues associated with M-pass filters. First, they only offer a 20 dB roll-off for filtering of close-in blockers. Second, the amount of attenuation at far-out frequencies is determined by the resistive division between the R-on and RS. With RS of 50 ohm and R-on of around 5 ohm, we can get only about 20 dB of out-of-band rejection. Of course, to achieve higher rejection, we need to reduce R-on by using larger switches, which in turn increases the power consumption of LO drivers and increases the LO leakage to the antenna. The second problem is the harmonic responses of the M-pass filter. For example, if we apply a signal at twice LO frequency, again we see that the signal fits very well with the duration of 8 LO phases, and each capacitor always observes and samples the same part of the sine wave. Consequently, different DC voltages are stored in the baseband capacitors, and the output node is the staircase approximation of the input signal. This means that we have another bandpass filter around the second harmonic of the LO frequency. Even if we apply a signal at the third harmonic of LO frequency, we see its staircase approximation at the output node. In general, the M-pass filter shows bandpass characteristics at any harmonics of the LO frequency. As a result, we update our model to include the harmonic responses of the M-pass filter. Here, the baseband impedance ZBB is shifted to n times omega LO with a scaling factor of 1 over m times sinc squared of n over m. It means that the magnitudes of the bandpass impedances at the higher harmonics are smaller. Moreover, there are no harmonic responses at the integer coefficients of m times FLO. We can partially resolve this issue by using a differential structure. This figure shows a conceptual implementation of a differential M-pass filter with its corresponding model. Note that the number of the switches increases by a factor of 2, but the number of baseband impedances is reduced to half, and each baseband impedance is connected to two 180-degree out-of-phase clocks. Moreover, by moving to the differential structure, the harmonic responses at DC and even harmonics of the LO frequency disappear. The next problem is the noise and blocker folding. The M-pass filter is a discrete time system with an effective sampling frequency of m times FLO. Consequently, due to the Nyquist effect, the noise and blockers located at m-1 omega LO and m plus 1 omega LO fold back on the top of the desired signal with a normalized gain of 1 over m minus 1 and 1 over m plus 1 respectively. Fortunately, employing a larger m increases the frequency of the closest folding component and reduces its folding gain. However, to avoid the folding entirely, similar to ADCs, we need to add an anti-aliasing filter before the M-pass filters. Considering the noise folding, the minimum noise figure of the filter can be calculated by this equation, which is the same as the insertion loss of the filter. Hence, the noise factor is very low and can be improved by a larger M. The next problem is a reciprocal mixing. We have a signal at FLO, but also a large blocker at FLO plus delta FP. Now the large blocker mixes with the LO phase noise at delta FP offset from the carrier and appears at the top of the desired signal, increasing the noise floor of the receiver and desensitizing the receiver. Unfortunately, the magnitude of the reciprocal mixing component can only be reduced by improving the LO phase noise or adding an external filter to attenuate blockers before the mixers. The power consumption of the frequency dividers and buffers for non-overlapping clock generation is mainly determined based on the maximum possible SNR degradation due to the reciprocal mixing. Note that the frequency Divider output noise can be largely removed by resampling its outputs with the master clock. The reciprocal mixing component is not only present in the baseband voltage but also at the RF port of the mixer. The reciprocal mixing, together with the desired signal in the baseband, mix with the positive sideband of the LO and appear at the RF port. Consequently, the undesired reciprocal mixing term is present both at the baseband port and RF port of the mixer. Alternatively, we can also build a notch filter by employing high-pass filters and transparency of passive mixers. We can model the notch filter with a parallel LC tank. At FLO, the tank impedance is high and the output voltage is almost zero. At other frequencies, either the capacitor or inductor provides a low impedance and Vout is the resistive division between RL and RS. In the next step, we employ the M-pass filter as a building block to synthesize a programmable high-order bandpass filter and to realize a magnetic-free circulator. To synthesize a bandpass filter, we always start with a low-pass filter and calculate its components values using a filter handbook. To convert the low-pass filter to the bandpass filter, we need to replace the capacitors with parallel LC tanks and inductors with series LC tanks. The corresponding values of the capacitors and inductors can also be calculated using these simple equations. By doing so, now we can have a sixth-order bandpass filter. However, the bandwidth and center frequency of this filter are fixed, and we need to use M-pass filters to make it programmable. As discussed earlier, we could model an M-pass filter with a parallel LC tank. As a result, the parallel resonators in the bandpass filter can easily be replaced with their corresponding N-pass filters. However, it's not obvious how can we implement the series LC tank with N-pass filters. To answer that, I need to introduce the gyrator operation to you. A gyrator is a two-port system with an admittance matrix of Y, where Y11 and Y22 are 0, and Y12 is equal to G1 and Y21 is minus G2. Now if you connect the second port of the gyrator to a load impedance ZL, the input impedance is equal to 1 over the product of G1, G2 and ZL. Consequently, this circuit works like an impedance inverter. The gyrator can easily be implemented in CMOS technologies using a feed-forward transconductance GM1 and a return transconductance minus GM2. Now if you place a load capacitor CL at the second port of the gyrator, its input impedance is inductive and is related to CL over the product of GM1 and GM2. If the noise of the gyrator is not dominant in your system, it is more area efficient and also power efficient to use a smaller load capacitor and lower transconductances to realize a particular inductance value. In practice, the parasitic input capacitance of the gyrator and the limited output resistance of the transconductances limit the performance of the realized inductor. On the right side, the equivalent lump element model of this circuit is shown. We have an undesired series resistance whose value is inversely proportional to the intrinsic voltage gain of the feed-forward transconductance and the value of GM2. We also have two undesired parallel components, RO2 and CP. At low frequencies, the input impedance is determined by the series resistor. At frequencies above the cutoff frequency of the gyrator, which is related to R series over L series, we enter the inductive region and the input impedance increases linearly with frequency. Note that the gyrator cutoff frequency must be smaller than the desired receiver bandwidth in order to see the effect of the inductor in the filter roll-off. At frequencies above the self-resonance frequency of the gyrator, which is related to 1 over root square of Cp times L series, the input impedance becomes capacitive and reduces linearly with frequency. Note that the self-resonance frequency of this circuit should be at least 5 to 10 times higher than the system bandwidth. There are also some strong trade-offs in the gyrator design. The undesired series resistance can be reduced by increasing GM1 and GM2 and increasing the size of those transconductances. However, this would also increase the parasitic input capacitance of the gyrator and accordingly reduce the inductor's self-resonance frequency. Interestingly, the impedance of a series LC tank is inversely proportional to the impedance of a parallel LC tank. Consequently, we can replace a series LC resonator with two gyrators and a parallel LC tank. We can also use these two simple equations to calculate the value of LP and CP based on G1, G2, CS, and LS. Let's go back to our 6th-order bandpass filter. To reach a reconfigurable architecture, first we replace the series resonator with gyrators and a parallel tank. Then we replace each parallel resonator with its equivalent M-pass filter. Therefore, as shown in ISSCC 2013 by Milad Darvishi, a high-order bandpass filter with programmable center frequency and bandwidth can be realized. Now we want to use N-pass filter concept to realize a magnetic free circulator. Circulators are widely used in full duplex wireless systems. The full duplex operation involves simultaneous transmission and reception at the same frequency, thus potentially improving spectral efficiency, link capacity, and the network latency. In this scheme, the transmitter is connected to the port 1 of the circulator, the antenna to the port 2, and the receiver to port 3. The signal can only travel in the clockwise direction, meaning that the transmitter power is radiated by the antenna, but the transmitter signal cannot leak to the receiver. In the integrated circuit technologies, the circulator can be implemented using two reciprocal branches and one non-reciprocal branch. In the reciprocal branches, it does not matter if the signal travels from left to right or from right to left. It always experiences the same phase shift, for example 90 degrees here. However, in the non-reciprocal branch, the signal direction is important. For example, if the signal travels from left to right, it experiences 180 degree phase shift. However, the phase shift is 0 degree in the reverse direction. Now, let's analyze port 1 to port 2 transmission. The transmitter signal experiences 180 degree phase shift while traveling the two reciprocal branches at the top. It also experiences 180 degree phase shift while traveling the non-reciprocal branch at the bottom. Consequently, the transmitter signals appear in phase at port 2 and S21 is close to 1. However, the situation is entirely different for port 1 to port 3 transmission. In the clockwise direction, the transmitter signal experiences 90 degree phase shift, while in the counterclockwise direction, it experiences 270 degree phase shift. Consequently, two received signals at port 3 are out of phase and cancel each other. As a result, S31 is ideally 0. The non-reciprocal branch can be implemented using a two-port M-pass filter, consisting of M baseband capacitors and two sets of switches driven by M non-overlapping clock phases. Note that there is a time shift of delta t between phi A and phi B clock domains deriving left and right switches respectively. The transfer functions of the magnitude of V out1 over Vin1 and V out2 over Vin2 are the same and show a bandpass response similar to an N-pass filter. However, when the signal travels from port 1 to port 2, it experiences a delay of delta t corresponding to a phase shift of minus phi. Phi is equal to omega LO times delta t. On the other hand, when the signal propagates from right to left, it encounters a delay of TLO minus delta t, or a phase shift of plus phi. Consequently, in this way, a non-reciprocal component can be realized. In the final implementation in this paper, the reciprocal branches are implemented using a lump CLC equivalent of a transmission line, and the phase shift between the left and right LO domains is 90 degree. The measure S21 shows a low insertion loss of about 2 dB and the reverse isolation is about 50 dB, thus demonstrating the circulator functionality very well. Now I want to switch the gear and develop a design guide for mixer-first receivers. In the conventional current mode mixer first receivers, each baseband impedance in the M-pass filter is replaced with a transimpedance amplifier consisting of an operational amplifier with a gain of -A, an input capacitor Cin, a feedback capacitor CEF, and a feedback resistor RF. The antenna is also modeled with a voltage source in series with a source impedance of Rs. Since only one of the switches is on at any moment, we can remove all R-on resistors in the baseband ports of the mixers and put one R-on resistor at the input port of the receiver. Then, due to the Miller effect, the feedback impedance can appear at the input of the transimpedance amplifier with a scaling factor of 1 over 1 plus A. Consequently, the baseband resistor is equal to Rf over 1 plus A, and the baseband capacitor is equal to Cin plus Cf times 1 plus A. Due to the transparency of the passive mixers, the baseband impedance is upconverted to RF with a scaling factor of sinc squared of 1 over M divided by M. Hence, I replace all the switches and baseband impedances with an RF impedance consisting of C equivalent in parallel with R equivalent. Now I am going to calculate the value of Cin, Cf, Rf, and the op-amp gain based on receiver's high-level specifications. First, I estimate RF value based on the input matching requirement. At in-band frequencies, C equivalent has high impedance and the input resistance of the receiver can be calculated by R-on plus the parallel combination of RSH and R equivalent. By using the R equivalent and RSH equations calculated in the previous slides, one can estimate RF value via this complex equation. Considering the fact that sinc squared of 1 over M is close to 1 and R-on is much smaller than Rs, RF value can be calculated by this simple equation, which is the product of M, A, and Rs. In the next step, I am going to calculate the receiver gain. At in-band frequencies, the receiver input impedance is equal to Rs. As a result, the input voltage is half of the source voltage and the input current is Vin over Rs. The RF current is then converted to the baseband current with a mixing factor of sinc of 1 over M divided by M. The baseband current flows into the RF resistor and realizes a baseband voltage with a value of A times Vin. Consequently, the receiver gain defined by the output voltage of the baseband amplifiers over Vin is equal to A, which is exactly the gain of the operational amplifier. Now I want to estimate the equivalent capacitor CEQ based on the receiver's 3 dB bandwidth. To do so, I need to calculate the Thevenin resistance seen by the equivalent capacitor, which is equal to the parallel combination of R equivalent, RSH, and Rs plus R-on. On the other hand, from the input matching requirement, we know that RSH in parallel with R equivalent is equal to Rs minus R-on. As a result, the Thevenin resistance can be estimated by the parallel combination of Rs plus R-on and Rs minus R-on. Considering that R-on should be much smaller than Rs, the Thevenin resistance is equal to 0.5 Rs. Consequently, the C equivalent is inversely proportional to Rs and the baseband bandwidth of the receiver. On one hand, C equivalent is related to the 3 dB bandwidth of the receiver. On the other hand, C equivalent is related to the input capacitor Cin and the feedback capacitor Cf. Now the main question is how to divide the C equivalent between Cin and Cf. In the first extreme case, we can remove Cin entirely and implement the required capacitor using Cf. Since Cf appears at the input of the transimpedance amplifier with a scaling factor of A, the occupied area due to the baseband capacitors is minimum for a certain bandwidth. However, as I will talk about that later, to deal with out-of-band blockers, the transimpedance amplifiers consume more power in this scenario. Moreover, the performance of the receiver is also more sensitive to the op-amp non-idealities. In the second extreme case, we remove Cf entirely and implement the required capacitor using Cin. Higher out-of-band linearity and less sensitivity to the op-amp non-idealities can be achieved, but at the cost of a significantly larger chip area occupied by baseband capacitors. To emphasize the importance of Cin on the receiver's linearity performance, let's analyze the mixer-first receiver at far-out frequencies. The input impedance of the receiver is almost zero at far-out frequencies due to the Miller effect of CF capacitor. Hence, the input current is equal to the voltage of the blocker divided by the sum of the Rs and Ron. The RF current is then converted to the baseband with the mixing gain. Since there is no Cin in this receiver, the baseband AC current flows into CF due to its lower impedance at far-out frequencies and eventually goes to ground or VDD through the transimpedance amplifier. In order to tolerate the blocker current, the DC current of the transimpedance amplifier should be larger than the blocker current. Otherwise, the op-amp's output saturates, thus degrading the receiver's out-of-band linearity. As a result, the total current consumption of the entire baseband amplifiers can be calculated by this simple equation, which is related to the blocker voltage and the source impedance. Now, if a portion of the required capacitor is implemented by Cin, a part of the baseband current flows into Cin and the other part goes to the transimpedance amplifier. As a result, the required DC current of the baseband amplifiers is reduced by the blue factor in this equation. As an example, if we choose Cin equal to Cf times A, the area occupied by the baseband capacitors increases by a factor of A over 2 compared to the previous case. However, for the same amount of B1 dB, the power consumption of the baseband amplifiers reduces to half. Or for the same amount of power consumption, the receiver's B1 dB improves by 6 dB. Up to this point, we consider an ideal op-amp with no bandwidth limitation. However, in practice, the op-amp bandwidth is limited due to its dominant pole omega p here. Indeed, the op-amp bandwidth limitation affects the input impedance of the transimpedance amplifier. In general, it is desired that Zin transfer function satisfies two conditions. First, Zin must be constant over in-band frequencies. Otherwise, we have impedance peaking and the input matching condition is violated at passband edges. Second, Zin impedance must go down at out-of-band frequencies, since based on the standard, the power of the blockers increases at higher offset frequencies. This plot shows the input impedance of the transimpedance amplifier versus the baseband frequency for different omega p over omega 3 dB ratios when Cin is much smaller than Cf. Without Cin, even with omega p over omega 3 dB of 10, Zin impedance does not drop at out-of-band frequencies between 100 MHz and 1 GHz, thus significantly degrading the receiver's blocker 1 dB compression point. When the required capacitance is only implemented by Cin, the sensitivity of Zin out-of-band impedance to op-amp bandwidth is considerably reduced. However, this scheme significantly increases the occupied area by the baseband capacitors. To simultaneously optimize the chip area and out-of-band linearity of the receiver, I typically choose Cin to be about 10 times larger than Cf. Moreover, the op-amp bandwidth should be at least 3 times larger than receiver's 3 dB bandwidth to avoid in-band impedance peaking. In the next step, I want to calculate a closed-form equation for the noise figure of the conventional mixer-phase receivers. First, I need to replace the noise sources in the transimpedance amplifier with the input referred noise voltage and noise current sources to be insensitive to the input impedance of the preceding stages. In the TIS, we have two noise sources. One is 4kT RF and the other one is the input referred voltage noise of the amplifier VNA. To calculate the input referred noise voltage, we should consider a source impedance of 0. In this way, the input referred noise current flows through the voltage source and does not affect the output. By following the calculations shown in this slide, the input referred noise voltage is equal to the amplifier's voltage noise. To calculate the input referred noise current, we should consider a source impedance of infinity. In this way, the input referred noise voltage does not affect the output. By following the calculations shown in this slide, the input referred noise current can be calculated by this equation It is related to the noise of the feedback resistor and also the amplifier. Note that the input referred noise voltage and noise current are correlated since the amplifier noise is present in both cases. By replacing the TIA's noise sources, we have this simplified schematic for our receiver. Due to the transparency of the passive mixers, the baseband impedance appears at the RF node with a scaling factor of gamma, where gamma is 1 over m times sinc squared of 1 over m. Moreover, it can be shown that the voltage noise source and current noise source can come to the RF port with a scaling factor of root square of gamma and 1 over root square of gamma respectively. As a result, we have the circuit schematic on the right side to calculate the noise figure of the receiver. The noise factor of this circuit is estimated by dividing the total output noise by the portion of that noise caused by 4kTRS. After lengthy algebra, we reach this noise factor equation. Considering a large Rx voltage gain, the input matching requirement, and an Ron much smaller than Rs, the noise factor equation can be simplified to this one. The noise factor can be improved by three methods. First, reducing Ron by increasing the mixer size at the cost of higher power consumption for the LO drivers. Second, by employing a larger number of clock phases to increase the shunt resistance. However, this approach complicates the clock generation block and increases its power consumption. The third method is to reduce the amplifier noise by consuming more power in the baseband TIAs. Now I'm going to design a mixer-first receiver step by step using the calculated equations in the previous slides. In this example, omega LO is 1 GHz and the desired baseband 3 dB bandwidth of the receiver is about 10 MHz. A voltage gain larger than 30 dB and a noise figure about 3 dB are also desired. The output of this design guide is the size of the mixer switches, the value of Cin, Cf, and Rf, and the gain, bandwidth, maximum load capacitance, and the power consumption of the baseband amplifiers. We will also estimate the in-band IP1 dB and out-of-band B1 dB of the receiver. To do so, we need to know one technology-dependent parameter. The on resistance of a 1 micrometer over 14 nanometer device is about 1 kilo ohm in 14 nanometer CMOS technology. We start the design by determining the mixer size. As discussed earlier, the in-band input impedance of the receiver is 50 ohm and it reduces to Ron at far-out frequencies. Consequently, the rejection at far-out frequencies can be estimated by 20 log of Rs over Ron. To achieve 20 dB of rejection, Ron should be below 5 ohm. To minimize the parasitic capacitance of the switch and reduce the power consumption of the LO drivers, mixer switches must be realized by the minimum length transistors. Since Ron of a 1 micrometer over 14 nanometer transistor is 1 kilo ohm, the width of the mixer switches must be more than 200 micrometer in order to obtain a 5 ohm Ron for the mixer switches. As proved earlier, the receiver gain is equal to the voltage gain of the baseband amplifiers. Consequently, the op-amp gain must be above 30 dB. The feedback resistor RF should be about 8.7 kilo ohm to satisfy the input matching. The total equivalent baseband capacitor must be around 130 picofarad to achieve the desired 30 dB bandwidth of around 10 MHz. As discussed earlier, by considering the trade-off between the chip area and the receiver linearity, Cin is chosen to be 10 times larger than Cf, leading to Cin of 30 picofarad and Cf of about 3 picofarad. Moreover, by considering the trade-off between the receiver power consumption and out-of-band linearity, the op-amp open-loop bandwidth should be at least 3 times higher than the filter bandwidth. For simplicity, I decided to use an inverter-based amplifier. Its gain is equal to the product of Gm over ID, VA, and LA. LA is the channel length of NMOS and PMOS transistors, and VA is the length-independent early voltage, which is about 10 volts per micrometer. To achieve a 30 dB gain, the transistor's length should be larger than 0.15 micrometer. However, this is not the entire story. To finalize the length of the transistor, we should also look at the transistor's flicker noise corner. By choosing a channel length of 0.15 micrometer, The flicker noise corner of the transistors can be above 10 MHz, which is more than the 3 dB bandwidth of the receiver, thus degrading the noise figure of the receiver dramatically. To avoid that, we increase the channel length of the transistors to 0.5 micrometer to achieve about 1 MHz of flicker noise corner. Then I estimate the required noise of the baseband amplifier using the noise figure equation. Considering a 3 dB noise figure, the amplifier input refer voltage noise should be below 8 kT/RS. On the other hand, the input refer noise of an inverter-based amplifier is equal to 4 kT gamma over Gm. Consequently, the inverter transconductance should be larger than 10 millisiemens. This plot shows Gm per width for different channel lengths for an inverter-based amplifier. Considering a Gm over W of 0.05 for the channel length of 0.5 micrometer, the total width of the transistors in the amplifier must be above 200 micrometer to achieve a Gm larger than 10 millisiemens. This plot shows Gm over ID versus different channel lengths for an inverter-based amplifier. Considering a Gm over ID of 15, the DC current of each baseband amplifier should be above 670 microamp to achieve 10 millisiemens of Gm. This results a total power consumption of 3.5 milliwatt for all baseband amplifiers, considering a 1.3 volt supply voltage. The maximum load capacitance of the op-amp can be calculated by knowing the 3 dB bandwidth of the op-amp. Omega P is related also to Gm over A times CL. As a result, CL should be below 1.8 picofarad, which is enough to directly drive a 10-bit SAR ADC. The in-band linearity of the receiver is limited by the last stage. The maximum voltage swing at the output of an inverter-based amplifier should be below VDD minus 2 VDSAT, which results in the maximum input voltage of around 15 mV and a P1 dB of minus 26 dBm. The maximum out-of-band input voltage of the mixer first receivers can be calculated using this equation as discussed in slide 58. All parameters in these equations are known except the amplifier gain at the blocker frequency. Considering a omega P of 30 MHz, a DC gain of 30, the amplifier gain is about 2 at the blocker frequency of 500 MHz from the LO frequency. Consequently, the estimated B1 dB of the receiver is about 10 dBm. Next, based on the calculated components values in the design guide, I simulated the mixer first receiver in cadence. The simulated gain of the receiver is 29 dB, which is very close to the required value of 30 dB. S11 is about minus 30 dB at 1 GHz LO, proving the receiver matching to 50 ohm. The simulated bandwidth of the receiver is about 8 MHz, which is slightly lower than the desired value, since I did not consider the amplifier's input parasitic capacitance in the bandwidth calculations. The simulated receiver noise figure is around 3.2 dB, and the noise figure increases at offset frequencies below 1 MHz due to the flicker noise corner of the baseband amplifiers. The simulated IP1 dB of the receiver is minus 24 dBm, which is slightly larger than the estimated value in the design guide. The simulated B1 dB of the receiver is plus 10 dBm, which matches very well with the analytical calculations. To simulate the in-band and out-of-band IIP3 of the receiver, I applied two tones at the input of the receiver, one at FLO plus delta F, another one at FLO plus 2 delta F minus 2 MHz. Then I swept delta F from 4 MHz to 400 MHz. As you can see here, the receiver's IIP3 at far out frequencies is about plus 17 dBm. To conclude this part, as demonstrated here, we could design the entire receiver using the developed design guide, and simulation results in cadence are in good agreement with the analytical calculations. Now I want to discuss the issues related to the traditional mixer first architecture. To do so, first I need to remind you of the importance of having a large loop gain in the feedback systems. Without any feedback, the amplifier's input-output characteristic can be modeled by this equation where alpha 1 is the amplifier gain and alpha 2 and alpha 3 are the second order and third order nonlinearity coefficients. As a result, the amplitudes of the second order and third order input intercept points can be estimated by these two equations. On the right side, we put the same amplifier in the negative feedback scheme with the linear feedback factor of beta. After lengthy algebra, we can show that the amplitudes of the second order and third order input intercept points in the closed loop system are proportionally improved by the loop gain. The loop gain is the product of the amplifier gain and the feedback factor. Consequently, having a large loop gain is essential to achieve high in-band linearity. Let's calculate the loop gain of the first order transimpedance amplifier. Here Rm is the load resistance seen at the baseband port of the mixer. To calculate the loop gain, we need to break the loop at the input of the amplifier and calculate Vout over Vin transfer function. Of course, the loop gain is a function of the op-amp DC gain and Rf and Rm values. However, interestingly, the loop gain transfer function has one zero at 1 over RFCF and two poles, one related to the op-amp 3 dB bandwidth and the other one is related to Cin plus Cf times parallel combination of Rf and Rm. To get more insight, this plot shows the Bode diagram of the loop gain. At very low offset frequencies, the op-amp DC gain A0 and the ratio of Rm to Rm plus Rf determine the loop gain. Note that Rm should be much larger than Rf to achieve higher loop gain. At a frequency much lower than the filter's 3 dB bandwidth, we have a pole that reduces the loop gain by 20 dB per decade. We also have a zero located slightly above the receiver's 3 dB bandwidth. Since the loop gain significantly drops at the passband edges, we expect worse linearity at those frequencies in the first order transimpedance amplifiers. Let's go back and calculate the TIA's loop gain in the conventional mixer first receivers. Since the mixer is on only 1 m's of the time, the load resistance seen at the mixer baseband port is m times larger than Rs. On the other hand, from the input matching requirement, we already know that the Rf is equal to m times A times Rs. By replacing Rm and Rf in the loop gain equation, the TIA loop gain in the conventional mixer first receivers is below 1, even at low offset frequencies. It means that we do not have or get any linearity improvement from the negative feedback in this structure. The problem originates from the fact that Rf is used to satisfy the input matching requirement. It is also well known that we need to have a virtual ground at the input of the TIA amplifier to reach higher in-band linearity. However, since RF resistor should satisfy the input matching requirement, half of the source voltage swing appears at the input of the TIA, thus degrading the receiver in-band linearity significantly. To resolve the in-band linearity problem in the conventional mixer first receivers, the feedback resistor RF is exempted from satisfying the input matching. Instead, an explicit resistor Rm is placed at the input of the receiver to provide input matching. Now, the signal swing at the input of the TIA can be calculated by this equation. Obviously, having a larger M or a bigger op-amp DC gain can help us to reduce the TIA's input impedance and its input voltage swing, thus improving the in-band linearity significantly. However, the noise figure of this receiver is at least 3 dB since we added an explicit 50 ohm resistor at the input of the receiver. To enable RM noise cancellation, David Murphy in JSCC 2012 added an auxiliary tone conversion path shown in blue to the mixer first receiver. For the sake of simplicity, only one of the mixers and baseband amplifiers are shown in each branch. The whole point here is that the desired signal appears differentially at the outputs of the main and auxiliary receivers, but RM noise appears as a common mode signal and therefore can be cancelled entirely. Let's first analyze this circuit for the desired signal. In this structure, the input impedance of the TIAs is very small. Consequently, the impedance seen at the RF port of the mixer is almost zero. As a result, the receiver input current is Vs over 2 Rs. This current is then converted to the baseband current with a mixing factor of sinc of 1 over M divided by M. The baseband current flows into RF and realizes a baseband voltage at the output of the main receiver, which can be calculated by this equation over here. Then we focus on the auxiliary branch. Its input voltage is equal to Vs over 2, which is converted to an RF current by the -GM cell and then converted to a baseband current and generates a baseband voltage at the output of the auxiliary receiver, which can be calculated by this equation over here. To have a differential output signal, RF1 must be equal to the product of GM, RS, and RF2. Let's do the same exercise for RM noise. Since the input impedance of the TIAs is almost zero, the receiver input current is minus VNRM over 2RS, where VNRM is RM voltage noise. The RF current is then converted to the baseband with a mixing factor and eventually realizes a voltage at the output of the main receiver, calculated by this equation over here. For the auxiliary path, the input voltage is VNRM over 2, which is eventually generates a baseband voltage at the output of the auxiliary receiver estimated by this equation over here. As we calculated in the previous slide, since RF is equal to the product of GM, RS, and RF2, RM noise appears in the common mode voltage at the outputs of the main and auxiliary receivers, and therefore can be cancelled entirely. Interestingly, it can be shown that the noise of the mixers and baseband amplifiers of the main receiver is also cancelled in this scheme. This slide shows the modified noise cancelling structure. The matching resistor and the GM transconductance are moved from the RF port of the mixer to its baseband port. In this way, the GM cell operates at much lower frequencies, thus improving its linearity and power efficiency. Moreover, the number of the mixers reduces to half, thus saving significant power in the LO buffers. Finally, the source impedance Rs, mixers, and the input capacitance of the GM cells form an N-pass filter, thus rejecting out-of-band blockers at the input of the receiver significantly. Next, I talk about the role of N-pass filters in improving the linearity of LNTA-based receivers. This slide shows the schematic of a conventional current mode receiver consisting of a transconductance with the feedback resistor of Rm, passive mixers driven by M non-overlapping clock phases, and M first-order transimpedance amplifiers. To satisfy the input matching, Rm should be equal to Rs times 1 plus GMRL, where RL is the load impedance of the transconductance. The noise figure of this receiver is proportional to 1 plus Rs over Rm. Considering the input matching requirement, the noise figure is inversely proportional to Gm times RL. It means that a larger GMRL is needed to minimize the receiver noise figure. However, on the other hand, the voltage gain of the LNTA is also related to GMRL, and to achieve high linearity, we need to avoid any voltage gain at the LNTA's output. However, this results in a large noise figure penalty. Since Rm is used to satisfy the input matching, there is a strong trade-off between the noise figure and linearity performance of this receiver. For the sake of simplicity, only one of the mixers and baseband amplifiers are shown in this schematic. To break the mentioned trade-off in the previous slide, Shin-He introduced a translational loop. It is formed by upconverting the inverted output voltages of the baseband amplifiers and feeding them back to the input of the receiver via Rm resistor and Cm capacitor. In this way, the transconductance feedback resistor or bias is exempted from satisfying the input matching requirement and can be chosen very large to have a negligible effect on the receiver noise figure. Observing from the RF input signal, the receiver is equivalent to a bandpass amplifier with a shunt resistive feedback. The receiver input impedance can be approximated by Rm divided by Grx, where Grx is the receiver voltage gain from the receiver input to the TIA's output. Hence, to satisfy the input matching requirement, Rm can now be much larger than Rs due to the high voltage gain of the receiver. Consequently, the noise contributed by Rm can be neglected. Note that the antenna impedance and Rm form a voltage divider, which attenuates the LO leakage generated in the upconversion mixers. Due to the receiver selectivity, the receiver gain drops outside the desired band. Consequently, the receiver's input impedance increases at the out-of-band frequencies, since it is inversely proportional to the receiver gain. As a result, far-out blockers appear at the LNTA input almost with no attenuation, thus degrading the receiver's out-of-band linearity and 1 dB blocker compression point. To reduce the receiver's input impedance at out-of-band frequencies, one can add an M-pass filter at the receiver input. Inside the desired band, the input impedance of the M-pass filter is large and the receiver's input impedance is determined by Rm over Grx. However, at far-out frequencies, the input impedance of the M-pass filter drops to Ron, thus realizing a low impedance at the receiver input and attenuating the blockers significantly. To achieve higher rejection, one needs to reduce Ron by increasing the width of the switches. However, this comes with a higher power consumption for the LO buffers and also increases the LO leakage at the antenna port. To get more insight on the LO leakage, consider this schematic. The falling edge of the first LO signal comes first and couples through parasitic capacitance to induce a negative pulse at the antenna port. After a short time, the rising edge of the second LO comes and causes a positive pulse on the antenna port. This doublet waveform repeats itself every TLO over M in a perfectly matched scenario. Consequently, the spectrum of the input port has some components at integer coefficients of M times FLO, which are far away from the desired Rx band. However, due to the mismatch between the parasitic capacitance of the switches, the shape of each doublet waveform will be different at each transition. However, the exact same waveform repeats every TLO cycle when the same switch is turned on again. This increases the LO leakage at FLO. Although the relative mismatch improves by increasing the size of the switches, the overall LO leakage power becomes higher due to the stronger capacitive coupling between the LO signals at input port. To reduce the LO leakage, we can employ a gain-boosted N-pass filter consisting of an amplifier with a gain of -AP and an N-pass notch filter in its feedback. As discussed earlier, we can replace the notch filter with its equivalent lump model, containing a parallel LC resonator operating at FLO and 2R-on modeling the switches on resistance. Due to the Miller effect, the feedback impedance appears at the input of the amplifier with a scaling factor of 1 over 1 plus AP. The receiver can be simplified to this schematic. In the desired band, the input impedance of the gain-boosted M-pass filter is high and the receiver input impedance is determined by Rm over the receiver gain. At far-out frequencies, the receiver's input impedance drops to 2R-on over 1 plus AP. Consequently, for the same amount of out-of-band rejection, the size of the switches can be reduced by a factor of AP over 2 compared to the previous case. This significantly reduces the power consumption of the LO buffers and decreases the LO leakage to the antenna. As a drawback, this structure only offers first-order filtering at the receiver input, thus limiting the receiver's out-of-band linearity for closing blockers. This is particularly a problem in 5G applications where the closing blockers are located near the passband edges. To improve the receiver's RF selectivity, Muntazir Qaim employed a third-order high-pass filter consisting of LH and CH capacitors and used the transparency of the passive mixers to realize a 6th-order notch filter in the feedback of the amplifier. Consequently, the filter slope at the input of the receiver increased to 60 dB per decade. The resulting baseband inductors can be implemented using gyrators and baseband capacitors as discussed in the gyrator section. Note that gyrator cutoff frequency should be smaller than the desired receiver bandwidth and its self-resonance frequency should be 5 to 10 times higher than the receiver bandwidth. At the end of the presentation, I would like to say some words about harmonic rejection in wideband receivers. Let's consider an LNTA-based receiver using 4 non-overlapping clock phases. Since there is no external band select filter at the receiver's input, the receiver must deal with the blockers at the integer coefficients of the desired signal, for example at 3 omega LO and 5 omega LO. In this structure, the effective in-phase and quadrature LO signals are square waves, as shown with the solid black line here. And they have components at omega LO, 3 omega LO, and 5 omega LO. Consequently, not only the desired signal at omega LO is down-converted to the baseband, but also the blockers at 3 omega LO and 5 omega LO mix with the third and fifth harmonic of the LO signals with a normalized gain of 1 over 3 and 1 over 5 respectively, and appear at the top of the desired signal. Hence, it degrades the receiver performance dramatically. This receiver can only offer 9.5 dB rejection for the folded blocker from 3 omega LO, which is insufficient in many applications, and we cannot do anything to improve that in the digital domain. To resolve this issue, this paper introduced the principle of the harmonic rejection mixers. Instead of having one mixer, we have 3 mixers in parallel, which their outputs are combined with amplitude weighting factors of root square of 2, 2 and root square of 2. The mixers are driven by 3 different LOs with a relative phase of minus 45 degree, 0 and 45 degree. If we look at the phasor diagram on the right side, at the fundamental frequency, the outputs of the mixers are added constructively, and we have the down-converted copy of the desired signal in the baseband. However, since the phase shift of the nth harmonic is n times that of the fundamental, at third and fifth harmonics the mixer's outputs are added destructively, and no signal folded from 3 omega LO or 5 omega LO can be observed in the baseband. Alternatively, we can analyze this system in the time domain, where the amplitude weighting combined with the phase shifting can be considered as a staircase approximation of a sinusoidal LO shown in green. This staircase LO signal has no component at 3 omega LO and 5 omega LO, and the blocker at 7 omega LO is now the first harmonic that is not cancelled. It is understood that the 45 degree phase resolution among different LO clocks is required to implement harmonic rejection. On the other hand, for 0 IF receivers, we need to have a high IIP2, so differential LO clocks are also desired. Consequently, to simultaneously achieve higher harmonic rejection, high IIP2, and baseband to RF impedance transformation, we need to use at least 8 non-overlapping clock phases. To reconstruct the staircase approximation of the in-phase and quadrature LO signals, the outputs of the mixers must be added with amplitude weighting factors as shown in red terms in this slide. In this paper, the authors implemented this idea by weighted combining the outputs of the baseband amplifiers using transconductance stages. At the receiver output, the folded blockers from 3 omega LO and 5 omega LO are cancelled. However, at the output of the baseband amplifiers and the input of the transconductance stages, the down-converted blockers are present, thus putting stringent requirements on the linearity of the baseband amplifiers and demanding large power consumption. Consequently, it is wise to reject harmonics in the current domain and before the baseband amplifiers, where we don't have any voltage gain. Consequently, the voltage mode amplifiers at the baseband ports of the mixers are removed, and the required weighting factors are implemented using transconductors at the RF ports of the mixers. As an example, Chen in ISSCC 2015 implemented this idea by using 3 transconductance stages with amplitude weighting factor of 1, root square of 2, and 1, and combined their outputs using different LO phases to reconstruct the staircase approximation of a sine wave LO signal. In this way, the I and Q output currents do not have any components from the blockers at 3 omega LO and 5 omega LO. In practice, the amount of harmonic rejection is limited by the amplitude and phase mismatch among different LO clocks and can be estimated by using this equation, where sigma A and sigma phi are the standard deviations of the gain and phase mismatches. Even when considering a sigma A of 4% and sigma phi of 0.5 degree, we can get about 40 dB of rejection, which is not enough in many applications. For multi-phase clock generation, it is common to use high-frequency master clock with low phase noise to provide the input clock for a frequency divider. To remove the random jitter originating from the frequency divider and reduce the phase mismatch among the generated clock phases, it is crucial to retime the multi-phase clocks with the master clock. The next question is how we can reduce the sensitivity of the harmonic rejection to the amplitude mismatch. The answer is to employ harmonic rejection in multiple stages. If we have an alpha % amplitude error in the first stage, the harmonic rejection is related to 2 over alpha. Now if we connect the output of the first stage to the second stage, which has a beta % amplitude error, the amount of the harmonic rejection is improved by a factor of 2 over beta. It means that the harmonic rejection error becomes the product of 2 errors, one from the first stage and second one from the second weighting stage. Even with a pessimistic weighting error of 10% in both first and second stage, the harmonic rejection will be as large as 52 dB. In fact, RU in ISSCC 2009 implemented 2-stage polyphase harmonic rejection to have less sensitivity to amplitude mismatch among different LO and signal paths. This structure also allows for approximation of the irrational ratio of root square of 2 accurately with 2 integer ratios. For instance, 2, 3, 2 in the first stage combined with 5, 7, 5 in the second stage. In contrast to irrational ratios, such integer ratios can be implemented using well-matched and identical components. As a result, this work could achieve more than 60 dB of harmonic rejection without having any calibration. To conclude my presentation, in fact, current mode receivers avoid any voltage gain before the baseband filtering to achieve high in-band and out-of-band linearity. N-pass filters show tunability, low loss, high linearity, and high quality factor. However, designers should deal with their undesired harmonic responses, noise and blocker folding, and also their reciprocal mixing. N-pass filters are frequently used in reconfigurable sub-6 GHz receivers, high-order bandpass filters, and magnetic-free circulators. Together, we also develop a design guide for the mixer-first receivers. Moreover, key techniques introduced in different state-of-the-art mixer-first and LNTA-based receivers are discussed. Thank you very much for your attention.